So I'd like to welcome you all. Each year we run a symposium primarily with outside people that are not part of the Enigma group, to understand better what we are missing and to help project to people outside of our community what we do in the Enigma program. So the Enigma program stands for the evolution of nanomachines in geosphere and microbes. So the core question that we're trying to understand, I don't know how far along we'll get in 5 years, but how did proteins evolve to become the predominant catalysts of life on Earth? And the Enigma team is large. It has approximately 45 researchers from across the world. And we divided ourselves into three themes. And these are not hard edges. These are just buckets in which postdocs can work or graduate students can work with a lead. But every one of the postdocs and graduate students has to, at least at some point, explore the other two themes. So theme one is led by Vic Nanda, who's in the Center for Advanced Biotechnology and Medicine and in the medical school in the Department of Biochemistry at Rutgers. He's an old friend of Drawer's. He was a postdoc with Delgado and at Penn, and while Drawer was across the hall, basically as a postdoc with Les. And the synthesis of the nanomachines is basically ultra small peptides, proteins that are catalytic. That's what we've been focusing on. Theme two is led by Jana Bromberg, and it is basically a bioinformatics approach to understanding the complexity of the nanomachines and microbial ancestors. And the third theme is co-led here at Rutgers by Nathan Yee and by Bob Hazen and Shawna Morrison at the Carnegie Institute in Washington. And that is a coevolution of nanomachines in the geosphere, focusing primarily on minerals. So the focus on enzymes is that we focus on the oxidoreductases rather than just all the enzymes in life, obviously. There are many, many, many enzymes we're leaving out. And why do we focus on the oxidoreductases? Because the evolution of metabolism is the key to understanding the origin of life, in our opinion. We are not in an RNA world here. And some of these enzymes are extremely ancient and they're highly conserved. And they're still found in, for example, in mitochondria, in many, many other prokaryotic cells. And our objective here is to reverse engineer their evolution to give rise into how these organisms obtained energy on early Earth using a very, very small subset of the protein sequences and or structures to try to understand the so-called Legos of life. Theme one is in what we would call prebiotic catalysis. Theme two is the evolution of the nanomachines, and theme three covers geologic time for all of Earth's history from approximately 4.5, but we really don't have any rock record from 4.5. So it, in effect, is from 4, which is the beginning of the Archean, to modern times. So the period from 4 to 2.5 is called the Archean. We had oceans. We had very little land mass at the very beginning of Earth's history. Continents were not yet formed. The so-called freeboard thought is that we had very little rock that was not in an aqueous phase. And of course, that changed over geologic time. And we got into, from 2.5 onwards, into what we call the Wilson cycles, or what is known as the Wilson cycles, which is a long-term 500 million year cycle of the accretion of continents and their breakup over geologic time. So that's the basic overview. Obviously, these images and our publications are in our website, which is www.enigma.rutgers.edu. I would now like to make a very simple comment that we have three speakers that are in Israel, and so they're at a different time zone than us. We had invited a fourth speaker, and that was Dan Twafik, who was unfortunately he is no longer with us. He died a few weeks ago. And I asked Dror if he would be able to give us a small remembrance of him. He was at the Weizmann Institute, and he would have been one of our first speakers today. So, Dror, it's yours.